All right, so here we go. We are going to be learning sections 8.4 and 8.5 from the Halliday and Resnick textbook. This section is great. Finally, we're going to tie everything that we've learned about work and energy together all in this one chapter. So we're going to learn how to deal with work done by external forces and deal with conservation of energy all within the same problem. All right, so here we go. All right, so, so in chapter 7, we learned the work kinetic energy theorem, and it said that if you calculate the work done by your net force, or your net work, that's equal to your change in kinetic energy, okay? More recently, we learned that if you calculate the work done by your conservative forces, that's equal to the opposite of the change in potential energy, okay? Now, this notation is a little bit weird. I'm not positive I've used this work before, or this notation before. So CONS here means conservative. So basically what this is saying is this. It's saying if you calculate the work done by gravity, that's the opposite of the change in gravitational potential energy. And if you calculate the work done by a spring, that's equal to the opposite of the change in elastic potential energy, okay? And so I guess technically I probably could have just written this. The work done by conservative forces, all conservative forces, including gravity and a spring, would just be equal to, oops, forgot my negative sign, would just be equal to the opposite of your change in potential energy, okay? All right, and so remember, the idea is as you use your potential energy, you're doing work, but you're going to lose potential energy and then add that energy in elsewhere, okay? All right, so the next thing to be aware of then is this, that if we wanted to calculate the net work, that's the total of the work done by all of our forces, right? Well, every force is either conservative or non-conservative. So if I calculate the work done by my conservative forces and the work done by my non-conservative forces and add them up, that's going to give me my net work, right? Okay, so let's clean this up a little bit. So what I want to do is, let's algebraify this. I'm going to just subtract this from both sides of the equation, and that gives me this, right? I'm just subtracting the work done by conservative forces. So I get the work done by non-conservative forces is equal to our net work minus the work done by conservative forces. Okay? Well, look, net work is change in kinetic energy. So I'm going to replace this thing with change in kinetic energy. And then I've got minus, well, the work done by conservative forces is negative change in potential energy. So minus a negative becomes plus the change in potential energy, right? Okay, well, look, if I find the change in kinetic energy and I find the change in potential energy, then that's the change in mechanical energy, right? Because all mechanical energy is either kinetic or potential, okay? Which gives us this. Oh, right. Okay, so I didn't write out the big result. So here's our big result. If you calculate the work done by non-conservative forces, that gives you your change in mechanical energy. All right, this is huge. All right, I use this all the time when solving problems. All right, if you identify what your non-conservative forces are, you know, maybe there's friction, maybe Roy's pushing the box, whatever. If you calculate the work done by those non-conservative forces, you're figuring out how much your total energy is changing. Okay? All right, and then finally, just a side note, this, the work done by kinetic friction, well, as your object slides, you're going to lose energy, right? Because of friction. And it turns out that you're going to lose mechanical energy because of that, right? So your work done by friction is always going to be negative, right? If your box is sliding this way, friction goes that way. So your work done by friction is going to be negative. So you're going to lose mechanical energy, and in return, you gain thermal energy. Okay? So the work by friction is negative, so that makes this positive. Okay? So this ETH is thermal energy. Okay? All right. So that accounts for sort of where the energy goes when there's friction. All right? Okay, so what you're going to see here is in solving these problems, there are going to be basically three ideas that are very, very central to what how I solve these problems. All right, so let me summarize those real quick. All right, so here are the three big things. So first of all, the work kinetic energy theorem. That gets used frequently. Okay. What I just told you, that the work done by non-conservative forces is equal to your change in mechanical energy. All right, and then finally, this, the idea of conservation of energy. Check it out. If there are no non-conservative forces doing work, if there are no non-conservative forces doing work, then the work done by non-conservative forces is zero, which means my change in mechanical energy is zero. So that means that my mechanical energy, my total mechanical energy, is constant. All right, that is huge. All right, so usually when we talk about conservation of energy problems, this is what we're talking about. We're talking about this idea that there are no non-conservative forces, so our total energy stays constant, right? So the classic example is that roller coaster problem, right? So whenever we do those roller coaster problems, we're assuming it's frictionless. So the only forces on this thing are gravity and normal force. But your normal force is always perpendicular to your direction of motion, so it doesn't do work, right? And so that's why those are conservation of energy problems. All right? So let's do an example, all right? So this is a two-part example. We're going to kind of do the same example twice. We're going to do it once without friction and once with friction, okay? So here we go. We've got a 3-kilogram block. So this little block here is going to be 3 kilograms, all right? And it's going to be launched up a frictionless inclined plane by a spring as shown in the figure. The plane is inclined at 30 degrees, and the spring constant is 800 newtons per meter. So A says if you press the block against the spring to compress the spring 0.2 meters, then how much work are you doing? All right, so to do this, we're going to have to calculate our gravitational potential energy, right? Because as the block goes up and down the ramp, our gravitational potential energy is going to change because our height is changing. So we need to pick a point in the motion of the object to represent a height of 0. All right, so a moment later, so here's the deal. Let me see if I can kind of redraw this. So there's the block now squished. Here's the block, 3 kilograms. And so between here and here, it's been moved 0.2 meters. All right, so I'm going to call this point here, the compressed point of the mass, I'm going to call that a height of 0. Okay, so everything is going to get measured from the compressed point of the block. All right, now worth noting, something that makes this problem a little bit easier is that since this angle is 30 degrees, at any given point, if I call this my delta x, and I call this height, my height is always going to be half of my delta x, right? Because it's a 30, 60, 90 triangle. Okay, so there are going to be a bunch of times where we find the height and double it to find the distance, or we know the distance and chop it in half to find the height. So just know that that's going to be a trick that I'm going to use a couple times as we solve this problem. All right, so here's the deal. So for part A, so before you press the block, okay, let's figure out what our mechanical energy is. So our mechanical energy is going to be, well, let's see, what kind of energy does it have in this first drawing before I push it? Well, it's going to have gravitational potential energy. We are assuming that the spring is not, we're assuming that the spring is not being compressed at all at this point. So all of our energy at this point is gravitational potential energy, okay? So let's figure out how much that is. And I know some of you guys at this point are thinking, wait a minute, isn't the weight going to squish the spring a little bit? And it will, and I'll deal with that in just a second and explain to you why it doesn't really matter, okay? So our mechanical energy, when the mass is just sitting here before the spring is compressed at all, is going to be m times g times h, right? So our mass is 3 kilograms. Our g is 9.8 meters a second squared. Our height at this point is going to be half of the 0.2, so 0.1 meters, right? So if you figure this all out, you end up getting 2.94 joules. All right? So what's going to happen now is when you let go of the box, when you let go of the box, gravity is going to pull it down, and it is going to squish the spring a little bit. But all that's happening then is that's gravity doing work, right? So all we're doing is we're converting some of this gravitational potential energy into elastic potential energy, but because gravity is a conservative force, it's still the same total amount of mechanical energy, okay? So before you squish it, this is how much mechanical energy we've got. All right. Now, after you squish it, now our mechanical energy is, well, we've compressed it, so now we're at a height of 0. So now our mechanical energy is all elastic potential energy, right? So that's 1/2 kx squared. So 1/2, our k is 800 newtons per meter. Our x is 0.2 meters. Don't forget to square it. Figure this out and you get 16 joules. All right, so look, our mechanical energy went up. Why? Oh, because you are a non-conservative force, right? So the work done by you is equal to the work done by all the non-conservative forces, because you are the only non-conservative force. Remember, frictionless. So that's equal to our change in mechanical energy, which for us is going to be what we ended up with minus what we started with, which gives us 13 joules after you round out your significant figures. Okay, so there you go. That is how much work you are doing, 13 joules. Okay. All right, so let me clean up the board a little bit here. All right, now in part B, now you're going to let go of the block, right? So we're here, so I guess we should write down. So at this point, we know that our mechanical energy here is 16 joules, right? Because we figured that out a second ago, right? Okay, so now you're going to let go of the block. And all that's going to happen is the spring is going to push it up. That's a conservative force. So gravity is going to be working against it, also a conservative force, right? But so the spring is going to launch the box up the ramp. So a moment later, oops. So a moment later, the block is going to be, way up here, stop and come down. All right, and at this highest point, all of my energy now is gravitational potential energy. Okay, but the idea is, right now, after you let go of it, there are no non-conservative forces, which means that our mechanical energy is constant. So, at the top, at its highest point, my mechanical energy is going to be, well, let's see, the spring isn't squished anymore, so there's no elastic potential energy. It's not moving because it stops at the top, so there's no kinetic energy. So all of my energy is gravitational. So that's mgh. And I know that my mechanical energy is still 16 joules. So I get 16 joules equals the mass times g times h. Solve for h, and you end up getting, it's like 0.544, right? And then remember, our displacement is just twice that, right? Because 30, 60, 90 triangle. So if you multiply that by 2, you get 1.09 meters. Okay? So I like this problem because it's both work. When you compress the spring, you are a non-conservative force doing work, changing the total energy of the system. And then after you let go of it, there are no non-conservative forces, so your total energy is constant. All right? So then that brings us to part C. Part C says eventually the block is going to come back down and hit the spring again. Well, and it says how far will it compress the spring before stopping? Well, as it comes down, there are, again, no non-conservative forces. The only force is going to be gravity and the spring, right? So what happens is when it slides back down the ramp, all of this gravitational potential energy, it slides down, it turns into kinetic energy. Then it hits the spring and it turns into elastic potential energy. And we're going to get back to the point where all of the energy is elastic, which is here, which means that you've compressed it 0.2 meters again. Okay? So this, theoretically, if this was a perfectly frictionless ramp, this would just keep happening forever, right? The spring would get compressed 0.2 meters, it would bounce back up the ramp, up to a distance of 1.09 meters, and then it would come back down, squish it 0.2 meters, go up 1.09, squish it, back and forth forever. Okay? All right, what if we add in friction? All right, so we're going to do the same problem, but this time we've got a coefficient of kinetic friction of 0.25. Okay, so some of the same questions, all of the same questions plus one extra step down at the end. Okay, all right, so exact same setup except now we've got friction. So A says if you press the block against the spring to compress the spring 0.2 meters, how much work are you doing? And notice here, this time the answer turns out to be 14 joules, right? which is more than the 13 joules we had before. But that should make sense, right? Because you have to do extra work to squish the spring, to compress the spring, to overcome the friction. All right? So here's what we're going to do. Before you squish it, I keep saying squish, I'm sorry if that's driving you bonkers. Before you compress the spring, all of the energy is gravitational potential energy. So it's the same calculation that we did before. All right? So before, our mechanical energy is equal to gravitational potential energy, which is mgh, which is still 3 kilograms times 9.8 meters a second squared times 0.1 meters, and it gives you 2.94 joules. All right? All right. Now, after you squish it, we've got mechanical energy, right? So 1/2 kx squared. Again, this is the same calculation we did before. So 1/2 times 800 newtons per meter times 0.2 meters squared, and it gives you 16 joules. Okay? So my change in mechanical energy is, again, 13 joules, right? That is equal to the work done by non-conservative forces, which is equal to the work that you do plus the work that friction did. Aha! So the problem here is we don't know how much force you're exerting, but we can find the force of friction. All right, so the idea is this. We've got our block on an inclined plane, right? So it's 3 kilograms. All right, we know this is 30 degrees. So if you go through and put in your find your force of gravity is going to be 29.4, but then you have these components, right? So the perpendicular component ends up being 25.46 newtons. The normal force turns out to be 25.46 newtons. Your parallel component of, your parallel component of gravity ends up being negative 14.7 newtons, and now I can find my force of kinetic friction. Right, just by doing my coefficient times my normal force. And the force of friction ends up being 6.63, it ends up being 6.365 newtons. All right, and I'm not going to make it positive or negative because it's going to depend on which way the box is moving. All right. So at the beginning, it's moving down, so my kinetic friction is going to be up, all right? But we are going to use that number a whole bunch, okay? So in fact, let's put it up at the top of the page so that when I erase, I'll still have it. So the kinetic friction is 6.365 newtons, okay? Sometimes positive, sometimes negative. All right, cool. So let's clean this up. We don't need this anymore. I'm going to want that space in a minute. All right, so now I can find the work done by friction, right? So the work done by friction is, well, that's the force of friction times the displacement, right? And they're anti-parallel, right? The box is moving down, friction is going to be up, okay? So, and this is all kinetic friction, right? So let's see, the work that friction is going to do, so our force of friction is going to be 6.365 newtons up the hill, and our displacement is going to be negative 0.2 meters because it's down the hill. And so you end up getting negative 1.273 joules. So now I can find the work that you did, right? So let me extend this. All right, so here's what we've got. We've got 13 joules equals the work of you plus the work of friction. So 13 joules equals the work of you plus the work of friction. So add 1 joule, 1.273 joules to both sides, and you find that the work of you is, it's like 14 point whatever, you know? All right, so there we go. There's the work that you did. Cool? All right, so that is part A. Okay, so now part B. Bam. All right, so part B. So what we figured out in solving that was that at the point when the spring is compressed to its maximum, we know that our mechanical energy here is 16 joules. Okay? Now, B says if you release the block, how far will it go up the ramp before stopping? All right, so this is the deal. All right? So, after you let go of it, the block is going to slide up the ramp, right? So it's going to go up the ramp, stop, and come back down, right? So here's the point where it stops. All right. So after you let go of it, the block is going to slide up the ramp, and friction is doing work. But now friction is your only non-conservative force, right? So here's what we know. At the bottom, our mechanical energy is all the elastic potential energy. That's the 16 joules. All right. When it gets to the top, our mechanical energy is going to be all gravitational potential energy, so mgh. So mg times h. So, but I want to write it in terms of delta x, okay? So this is actually, remember, your height is half of your delta x. So this is 1/2 mgx. Okay? All right. Now, cool. So the work done by friction is going to be our change in mechanical energy, right? Because work is our only non-conservative force, right? So the work done by friction is going to be, as it slides up, friction is going to go down. So this is, oh, here, let me write it out. So here's what we get. So the work done by friction is going to be the force of friction. I guess I should be putting K's here. So the force of kinetic friction times how far it goes. So that's the work of friction. That's got to equal my change in mechanical energy, which is final minus initial. So that's 1/2 mgx minus 16 joules, right? Final minus initial. Okay? Oops. Okay. So we know everything in here except for x, right? So let's plug in our numbers. Let's see. Our force of friction is negative 6.365 newtons times x equals 1/2 times 3 times 9.8 meters a second squared, kilograms here, times x minus 16 joules. Oops. 16 joules. Okay? So I'm going to leave you guys to do the algebra. You can certainly solve this. The only variable here is x. And when you solve it, you end up getting 0.76 joules. All right? So, oh, joules. Holy cow, that's not right at all. Let's try that again. 0.76 meters. All right? And remember, we're measuring from, we called our height of 0 at this point here where the spring is compressed. So that's also going to be a position of 0. So that's why the displacement here is measured above the compressed spring. All right? So now, let's do part C. So, this is probably the longest video I've ever made, so I apologize here. All right, here we go. Part C. Eventually, the block comes back down and hits the spring again. How far will it compress the spring before stopping? All right, so the idea is, if you go back, oh shoot, I wish I hadn't just erased all of that. A minute ago, we had figured out that at the top, our gravitational potential energy was, well, it's mg times half of x, right? So we had 1/2 mgx. Right, so let's figure out what that is. So our mass is 3, our gravity is 9.8, times 1/2 of our x, which we just figured out was 0.76 meters, right? So if you figure out the gravitational potential energy that it has up there at the top, you get 11.16 joules. Okay? All right, so that's at the top. Now, when we get to the bottom, we're going to have two kinds of energy, right? Because friction is going to slow it down. So the spring is not going to squish the full 0.2 meters. So at the bottom, we're going to have some elastic potential energy at the bottom, and we're going to have some gravitational potential energy. Okay? So for us, that's going to be 1/2 kx squared. That's the elastic potential energy. And my gravitational potential energy is going to be mgh, right? So this is going to be a little bit confusing. So here's the deal. So this distance here is 0.2 meters, right? Here's my x, right? That's how far the spring is going to get squished. Okay, so this distance here is 0.2 minus x, which means that my height there is half of that. So 0.1 minus a half of x, right? Okay, so that is our mechanical energy when we're at the bottom. Okay, so let's clean up the board a little. All right, so now we're going to do the same thing we did before, which is this. The work done by friction then is going to be our change in mechanical energy, which is final. So that's this mechanical energy we just wrote, 1/2 k x squared plus mg times 0.1 minus 1/2 x. So that's how much mechanical energy we start with, right? Final minus initial. And our initial is the gravitational potential energy we had at the top, so minus 11.16. Okay, so now the last thing we got to do is come up with an expression for the work that friction did. Okay, so as the box slides down the ramp, friction is going to be uphill. So my force of friction is going to be, well, no, let me do this. Work of friction kinetic. So the work of friction kinetic is going to be the force of friction, which is 6.365 newtons, times the distance it slides down the ramp. All right, so remember, the block went up 0.76 meters above the compressed point, which means that it is sort of 0.56 meters above the uncompressed spring, right? So the distance it's going to slide is it's going to slide back down that 0.56 meters until it hits the uncompressed spring, and then it's going to slide another x, right? Remember, x is how far the spring gets squished, okay? I don't know if maybe this makes more sense. It's going down that far, okay? So it's going to go down a distance of 0.56 plus however far it squishes the spring, okay? So that equals all of this, 1/2 k x squared plus mg times 0.1 minus 1/2 x minus 11.16. All right, so we know everything in this equation, all right? So you do a whole bunch of algebra that I'm not going to write out here, but you end up getting this. You end up getting 0 equals 400 x squared minus 8.335x minus 4.6556. And then you plug that into the quadratic formula, and your x ends up being 0.1188 meters. All right, so that is part C. Okay. All right, so finally, part D says eventually the block comes back down. Oh, no, sorry, D rather. How much heat energy is created from the moment the box is released until it stops again at the bottom? Okay, so there are two ways of doing this. So let me erase the board here. There we go. Okay, so how much work is done by friction? All right, so there are two ways of doing this. Option one. After you let go of it, the only non-conservative force is friction, right? So remember, the work done by kinetic friction is equal to our change in thermal energy, right? So really, we're just trying to figure out how much work friction did, okay? So for us, the work that friction does is equal to our change in mechanical energy, right? We lost mechanical energy and gained heat energy. So option one is figure out, let's see, when we released it at the beginning, at the very beginning, we had elastic potential energy totaling 16 joules, right? And then at the end, it stops. And remember, it had elastic potential energy and gravitational potential energy, right? based on the numbers we just got. So if you use that x that we just found and you calculate your elastic potential energy and your gravitational potential energy, you should get 5.64 joules of elastic plus 1.19 joules of gravitational for a total of 6.83 joules. So that means that we lost, what is this, 9? So our change in the mechanical is negative 9.27 joules, right? Oh, no, sorry, did the math wrong there. 9.17 joules. So that's how much mechanical energy we lost, so that's how much friction, how much heat energy we gained. Somewhere here I lost a little bit due to rounding. I'm not sure what happened there, but you know, within your 2 significant digits that we're given, we're still good. Okay? Now, the other way to do it is this. We know how far the block went up the hill and then back down the hill, right? So the block went up 0.2 meters to uncompress the spring. It went up another 0.56 meters from there, right? That was the total of 0.76. Then it's going to come down 0.56 meters, and then it compressed the spring another 0.12 meters. Okay? So, and friction is acting against all of that. So the work done by friction should be our force of friction, which is negative 6.365 newtons, multiplied by that total distance there. So if you add all of those up, let's see, 0.56 and 0.56 is 1.12, 1.24, 1.44 meters, I think. All right, I just did that in my head. I didn't write the numbers down, so double check my math there. But anyway, if you add up all these distances and multiply this out, it should give you the same answer that we just got, 9.16 or 9.17 joules. All right, there you go. All right, so that's it.